Hello there, my name is Charles Sipa. Welcome to another presentation on differentiation. I hope by now you've seen that we've gone through all the derivatives of elementary functions, be they exponential, polynomial, logarithmic, or trigonometric. Now what we want to do, we want to look at differentiating combination of these functions. Like for example, we've already seen that a derivative of sum of two functions is the sum of derivatives. Now we want to look at products of two functions, and later we're going to look at quotients of two functions. So let's start with an example of a function like this one, where we're differentiating f of x equals to x squared times cosine. So we know that the derivative of this function, in this case, what we're going to do here, we're going to derive this derivative using the first principle. This is not a proof, but a kind of an illustration of how the derivative of a product will work out. So if you want to see the proof, the formal proof is there in any standard text, including your textbook. So now the derivative of f of x will be df dx equals to the limit of the incremental quotient as delta x is approaching 0. That in this case we're going to put here f of x plus delta x minus f of x over delta x. Now evaluating this expression in terms of the function, we obtain something as follows. Of course, here now we're evaluating x, we get x plus delta x squared plus cosine of x plus delta x minus x squared times cosine x. I think you can see that this binomial expression will expand to that, and the cosine using the identity will get that, and we'll subtract that. Of course, this now will involve a tedious calculation of removing the brackets here, which I've done in a kind of a short way somehow. What I've done here, I've multiplied this first term by the first one here to get x squared cos x cosine delta x, and then multiply it there and got 2x delta x cos delta x. Then after that I stopped and took this term and multiplied the leading term there, which gives us minus x squared sine x cosine x times delta x. Then secondly, multiplying this by the second term, I get 2x delta x sine delta x. So what is left now is to multiply this bracket by delta x. So I've just put here delta x multiplied by the bracket. I hope you see what fitting bracket there, minus x squared delta x. Now if we analyze briefly limit as x tends to 0, you will see that this delta x here will tend to 1, then which will lead to the simplification of this term and that term. And then nextly, we are left with this term here and that. And if we analyze this one, you will see that this one tends to 0 faster than delta x, because there's delta x here and there's sine delta x, which the two of them there, they tend to 0. So this goes very fast to 0. And then lastly, turning to this bracket, you see here that delta x squared also tends to 0 faster than delta x. So this term here will also tend to 0. So what we're going to left in this quotient is the following. We write limit as delta x approaches 0 of the following expression. In this case, what we're left in the numerator, we're left with the 2x delta x cosine delta x minus x squared sine x sine of delta x over delta x. Now, simplifying this expression as x is delta x tends to 0, we can see that here this is a common denominator of 2. This one will simplify with that, and then here we're going to have our special limit as delta x is approaching 0 of sine delta x over delta x, which is equals to 1. So rewriting this in a different way, we would write the following. We know if we split this, the common denominator here, this will simplify with that. Then we are actually looking at the limit as delta x is approaching 0. After simplifying this and that, you get 2x cosine x cos delta x minus x squared sine x all over 1 multiplied by sine delta x over delta x, and you put this in brackets. So now, after having looked at this expression here, we can see that this is going to be 1 approach 1, and the cos of delta x here is going to approach 1 also. So the limit here is going to be 2x cosine x minus x squared sine x. But I would like to write this expression in a more suggestive way. This expression will be the derivative of f with respect to x equals to 2x cosine x plus x squared in brackets minus sine x. I'm writing this way so you can see what I would like you to see very clearly. Now, let's see where we started. We started with f of x equals to x squared cosine x. Note that we've got two functions there. You can say one function is u of x equals to x squared, and you know its derivative is equals to 2x. The other function is v of x equals to cosine of x, and the derivative v prime is equals to minus sine x. So now what we've got here, it looks like we've got u prime, which is there, u prime is 2x multiplied by v plus u x squared here multiplied by the derivative of v. So that takes us to what we call product rule for differentiation. In this case, we're looking at the case whereby we're having a function which is a product of two functions, let's say u by v, and we're differentiating that, and what will come out is that we'll get derivative of this being such kind of combination of the individual derivatives which appear in the function there. So summarizing this is what we get. So we've got a product h, which is uv. Now to find the derivative of h, which we denote here by dh, we have to get the derivative of u multiplied by v plus u multiplied by the derivative of v. Or writing in other terms, what we have, if you've got f of x multiplied by g of x, if we need the derivative prime there, we have to have f prime multiplied by g plus f multiplied by g prime. So I hope this is a clear rule. We call it the product rule. Others, now with that, you can now try the following examples applying the product rule. In other words, differentiate, find the following derivatives using the product rule. I hope this is a very clear rule and it's easy to apply. At this point, then I would like to sign off and say thank you for listening.